everyone. I'm Sujani, faculty in physics at Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss the tutorial question bank in module 4 of engineering physics, that is light and optics. So first let us look at the short answer questions in light and optics. We are going to look at short answer questions of 2 marks. So the first question here is, explain the principle of superposition of waves in case of 2 or more waves traveling simultaneously in a medium. So what is the answer for this question? When 2 waves arrive at a point simultaneously, they superimpose on each other and the amplitude of the resultant wave is the vector sum of the individual amplitudes. So let us understand this definition. We have 2 waves. The first wave of displacement y1 and this is the second wave whose displacement is y2. And if these 2 waves arrive at a point simultaneously, they will superimpose on each other. This is the term that is important. When they superimpose on each other, the resultant at that point is the vector sum of the individual amplitudes. So this is the resultant wave. So y is equal to y1 plus y2. So here we have considered for 2 waves. If there are more number of waves, it is the resultant of all the waves if they are arriving at a point simultaneously. Now the next question, what is the concept of interference of light and different types of this phenomena? So first we'll have to define what is interference and then we will also talk about the different types of interference. So first let us see interference. When 2 waves of the same frequency and having constant phase difference, so these 2 terms are important. They should have the same frequency and there should be a constant phase difference and moving in the same direction, superimpose on each other. Interference takes place. So we are talking about superposition before. So now the same principle, if we are considering, they should have the same frequency and a constant phase difference, then we get interference. So let us see the types of interference also. So if the 2 waves occupy the same space, means they arrive at the same point simultaneously, their amplitudes add. This is what we have seen in superposition. Now, depending upon how they interfere, they may interfere either constructively or destructively. So this is what we are going to see in interference. So depending upon how they interfere, if they are having the same frequency and having a constant phase difference, they may interfere either constructively or destructively. So if you see the waves here, this is the first one and this is the second one. Both of them are having the same frequency. Frequency here means the number of waves per second. They are the same and they have a constant phase difference, means crest falls on the crest and trough falls on the trough. Then in case of constructive interference, what we are seeing, the amplitude becomes maximum. So this is for constructive interference. So let us also see the destructive interference. So in constructive interference, what we have seen, it occurs at a point due to overlapping or intersecting of waves of the same frequency which are in phase. Means the crest falls on the crest and the trough fall on the trough. So in this case, what is happening? The 2 waves reinforce each other and combine to form a wave. And that has an amplitude equal to the sum of the amplitudes. The resultant wave has an amplitude which is equal to the vector sum of the individual amplitudes of the 2 waves. That is what we have seen. Y is equal to y1 plus y2. This is what we see in constructive interference. Now coming to destructive interference, it occurs when the 2 intersecting waves of the same frequency are completely out of phase. If the two waves have the same frequency, moving in the same direction, they have to superimpose on each other, but they are out of phase. So when they are out of phase means what? Crest falls on trough and trough falls on crest. In that case, what happens? Their amplitudes will cancel each other. So they will cancel each other. And how do we see the resultant wave? See, in this case, this last case, the frequency of the two waves is the same. They are moving along the same direction, but they are opposite in phase. Means wherever there is a crest here, we have a trough here. Crest means it is the maximum displacement in the upward direction. Trough here means the maximum displacement in the downward direction. So here, this is a crest, this is a trough. So in this, the crest is overlapping with the trough and the trough overlaps with the crest. So then what happens? They cancel out and this is the resultant wave or a null wave. So what we see in destructive interference is the resultant is 0. Now the next question, explain Young's double slit experiment. What is the experimental setup here? So what we see here in Young's double slit experiment is we have a source which we take a monochromatic source of light. This is a monochromatic source. Monochromatic source means light of a single wavelength. This light is allowed to pass through two slits. S1 and S2 are the slits, two slits. And these two slits are placed equidistant from this slit. So the rays that arrive at these two slits will be in phase with each other. So these two will now act as coherent sources. They will act as coherent sources. Now, according to Huygens principle, these slits will send waves and they will superimpose on each other according to the superposition principle we have seen. And they are superimposing on each other. The resultant is what we have on the screen. This is the screen on which we capture the spectrum. What we have here is a series of bright and dark fringes. So, bright fringes correspond to constructive interference and the dark fringes correspond to destructive interference. So let us see and understand what is there here. The interference pattern of dark and bright bands. Bands or fringes mean the same. They are produced by light passing through two closely spaced narrow slits. So these two slits should be closely spaced and they should be narrow. And it can be explained by the addition or superposition of wavelets originating from the two slits. So the waves that are coming from these two slits are superimposing, and depending upon how they superimpose on each other, we have constructive and destructive interference, which gives rise to bright and dark bands. This is what was explained by Young's double slit experiment. Now the next one. Monochromatic light from a narrow slit falls on two parallel slits and the interference fringes are obtained on a screen. Show this experiment with the sketch. So you have to show the experiment with the help of a neat diagram. So what is the diagram for this? This we have already seen. The setup we have seen. Now we'll see how the fringes are formed. So this diagram illustrates how the fringes are formed. So we have imagined that the source is here exactly. So the source it's not here. Exactly at the center, I told it is equidistant. The two slits are placed equidistant. Source. So light from this source is reaching this slit and also this slit, equidistant. Now these two slits which are narrow and closely spaced will act as coherent sources, S1 and S2. Now S1 will start sending out waves. S2 also will start sending out waves. Now these two waves will superimpose on each other. So you see here the one wave coinciding with the other, superimposing on the other. So depending upon the superimposition, if a crest falls on a crest and corresponding to that we have a bright fringe. So at the center, because we have the crest falling on the crest, the center fringe, this fringe is always a bright fringe. Now the interference due to this is destructive, means here in this region crest falls on the trough. So here we get a dark band. So what we have here on the screen is a series of bright and dark bands following each other, and we are going to number them also. On this side we are numbering the bright fringes. If this is m is equal to 0 is a central bright fringe, m is equal to +1 and +2. First bright fringe, second bright fringe. And here we are naming them as -1 because we are considering in the downward direction. So upward direction it is positive, downward direction it is negative. Now how do we number the dark fringes? If we are taking this as the central fringe, m is equal to 0, this is m is equal to +1, the first dark fringe, this is the second dark, and the dark fringe in the downward direction. So this is how the fringes are formed in Young's double slit experiment. Now what are the conditions for constructive interference? We have simply named that if the crest falls on the crest and trough falls on the trough. And there is a condition in which a crest falls on the crest or a trough falls on the trough. So for a bright fringe produced by constructive interference, so whenever there is constructive interference, we get a bright fringe. How we are getting a bright fringe? Because the path difference must be either 0, means there should not be any path difference between the two waves arriving at that point, or the path difference should be an integral multiple of the wavelength lambda. So what we are trying to understand here is, if we are talking about the path difference can be 0, means there is no difference in the path traveled by the two waves arriving at that point simultaneously, or the path difference should be an integral multiple of lambda. So path difference can be n lambda. So we are denoting the path difference by delta. So delta is equal to n lambda, where n can take the value 0, plus or minus 1, plus or minus 2, and so on. And n here represents the order of the number. So when we are talking about n is equal to 0, it is the 0th order maximum. Like we have seen in the previous slide, m is equal to 0 we have considered. And for n is equal to plus or minus 1, we call it as first order. +1 in the upward direction and -1 in the downward direction. Now let us see the conditions for destructive interference. So when destructive interference occurs, a dark fringe is observed. So destructive interference always gives rise to dark fringe. So what is the condition for the dark fringe or for the destructive interference? So the path difference is an odd multiple of half the wavelength. Means when we are writing the path difference, I'll write the path difference as 2n plus 1 into lambda by 2, where n takes the values 0, plus or minus 1, plus or minus 2, and so on. So let us put n is equal to 0. So when n is equal to 0 here, we get lambda by 2. Now when n is equal to 1, 2 into 1 is 1, 1 plus 2 into 1 is 2, plus 1, 3 lambda by 2. When n is equal to 2, we get 5, 2 into 2, 4, plus 1, 5 lambda by 2, and so on. So whenever the path difference is an odd multiple of half the wavelength, that is lambda by 2, then we get destructive interference. So we are writing delta. Delta denotes the path difference is 2n plus 1 into lambda by 2, or you can also write it as n plus 1 half into lambda, where n is an integer and n takes the values 0, plus or minus 1, plus or minus 2, and so on. Now next, define fringe width. What is fringe width? And also write the expression for fringe width. So let us first define fringe width or the bandwidth. So we may call it as fringe width or bandwidth. So the distance between any two consecutive bright or dark bands is called the fringe width. So whenever we are talking about the screen, we have a central bright fringe, M is equal to 0. Then you have a dark fringe and a bright fringe. So this corresponds to the bright fringe. This corresponds to the bright fringe. And in between there is a dark fringe. Now what we are saying, the distance between any two consecutive bright or dark fringes. So if I consider this point, this is the dark fringe starting, and this is the starting of the dark fringe between two dark or two bright. If I take this is the bright one and this is the bright fringe. So the distance between any two bright or any two dark fringes, we call it as the fringe width. Means what we do, we calculate the distance of the n+1th and the nth order consecutive bright fringes, and the difference xn+1 is the position of the n+1th bright fringe. Xn is the position of the nth bright fringe. So if we want to know the fringe width, what we have to do? We have to do xn+1 minus xn. So how do we get the expression for fringe width? So we will substitute the conditions d by d into n+1 into lambda. You need not derive this expression. In the long answer questions we are going to derive. We are arriving at the expression beta. Beta here represents the fringe width. Is equal to capital D by small d into lambda. Capital D is always the distance between the source, and screen. Between source and screen, we call it as capital D. And small d always represents the distance between the two slits. We are taking two slits which are very closely spaced. So the distance between two slits, we are denoting it by small d. And lambda here is the wavelength of light we are considering. So it is the wavelength of light. So knowing these three, you can very easily calculate the fringe width beta. Now fringe width between two maxima we have seen. Here we are talking about two minima. Minima here means the distance between two consecutive dark bands. So if you are talking about dark bands, we will put the condition for the dark band for x+1 dark fringe, xnth dark fringe, subtract. So what do we get again? Same. So what we understand here is the distance between any two dark fringes or bright fringes is the same, and we call it as fringe width. Now coming to the conditions for interference. What are the conditions for interference? Or to be specific, I say sustained interference. If the interference pattern has to be sustained, what are the conditions? So the two sources must be coherent. So how do we make them coherent? We are seeing that the light arrives at the two slits traveling equal distance so that they will be in phase. So they must maintain a constant phase with each other. Then we say they are coherent. Then the sources should be monochromatic. We should use light of single wavelength. Then the separation between the two sources must be small. We have talked about small d. Small d is the distance between the two sources. It should be very small. And then capital D is the distance between the source and the screen. It should be very large. So we have to keep the screen at a very large distance when compared to the distance between the two sources. Then the amplitude of the light waves must be equal. So we are taking two light waves which are superimposing on each other. Then their amplitudes must be the same. Then the two sources must be narrow. So they should be very narrow slits. then the two sources must emit light waves of same wavelength and same frequency. So this is the first condition for superimposition we have seen in interference. Then to view the fringes clearly, if you have to view these bright and dark fringes clearly, the background must be dark. So all these are the conditions for sustained interference. Next, what do you understand by diffraction of light? And then draw a neat diagram showing diffraction phenomena. So first we will understand what is diffraction and then we'll see the diagram. So what is diffraction? Light bends around the corners of the obstacles and enters into the geometrical shadow. So this is called as diffraction phenomena. And for this to occur, the size of the obstacle should be comparable to the wavelength of light. So you cannot see that if the size of the obstacle is big, you cannot see the diffraction phenomena. So what we are seeing here is, you see here, this is the object edge. There is an obstacle here. The light that is coming and falling on this obstacle is bending around the corners of the obstacle. So it is bending around the corners. And after bending, and according to Huygens, again, each point on the slit will act as a source and send out secondary wavelets, which will superimpose on each other, and you will get bright and dark fringes. So what we are trying to understand here is, if you imagine that this is the light that is coming and there is an obstacle here. So if you see that there should not be any light seen here because this is the obstacle. Okay, if you imagine light travels in the form of particles. So wherever you have the particles striking the screen, you will see the image. But here, because of the bending of the light around the corners of the obstacle, even you will see a diffraction pattern which will enter into the geometrical shadow. So light bends around the corners of the obstacles and enters the geometrical shadow. This is the meaning. So at the corners of the obstacle, the light will bend and it is entering the geometrical shadow, and you will have the diffraction pattern here in this region also. Now explain Newton's rings, how Newton's rings are formed. Newton is the name of the scientist who observed these rings first. So they are named after Newton. So what we are seeing here is, if monochromatic light is allowed to fall normally on a film and is viewed in the reflected light, we see alternate bright and dark rings with the concentric circles around the point of contact between the lens and the glass plate. So these circular rings are discovered by Newton, and then we are calling them as Newton's rings. So let me just explain you the setup. Suppose you take a plain glass plate and on this we place a plano-convex lens, which will just touch at that point. This is a plano-convex lens, means one side is plane and the other side is convex. So this is the point of contact. Now there is an air film that is trapped in between the lens and the plate, glass plate. If light falls on this setup and if you view the light, the reflected light reflected from this portion and which will transmit and get reflected from this portion, if these two interfere with each other, we get the interference pattern which consists of bright and dark fringes. And in this case, because it is symmetric, the air film is symmetric on both the sides. Here, it is the point of contact. So what we see here are rings like this, which you are seeing here. The central ring is the dark one, and then the bright, dark, and so on. They are concentric rings. Okay, so these rings are observed in the reflected light and they were discovered by Newton, and we are calling them as Newton's rings. Now, what is the experimental arrangement for Newton's rings, and what is the function of this glass plate G? We are mainly going to understand. The question here is, what is the purpose of this glass plate G? So this part I have already explained. We have a plain glass plate on which we are putting a plano convex lens. Now we are considering that light is incident normally on the setup. There is an air film that is trapped here. Now for light to be incident normally, what we do is we take a monochromatic source of light, that is the sodium vapor lamp. Light coming from this sodium vapor lamp is allowed to fall on a glass plate which is inclined, kept inclined at an angle of 45 degree. This glass plate G is kept inclined at 45 degree so that the light that falls on it is reflected like this, falls normally on the setup. And the light that is reflected is viewed with the help of this traveling microscope. So what we are doing here, the glass plate G is held at an angle of 45 degree with the vertical, and this plate reflects normally a part of the incident light towards the air film that is enclosed by the glass plate and the lens. And a part of this reflected light is reflected by the curved surface of the lens, and a part is transmitted, which is again reflected back. So when this falls here, a part of it is coming like this, part of it is being transmitted and again reflected. Now these two rays which are getting reflected are viewed with the help of this microscope, and because of the interference pattern we are able to see the Newton's rings. Next one, give the expression for the diameter of dark ring and bright ring. So we'll have to write the expressions for the diameters of dark and bright rings. So the expression for the dark ring here we can see is d square by 4 is equal to 2n minus 1 into lambda r by 2 after applying the conditions we have. We are not going to derive, we are only going to write the formula. So d is equal to under root 2n minus 1 into 2 lambda r. If we are writing for d, we can take 4 inside and take the square root. So we get d. Here lambda and r is a constant for that particular setup we are taking. So as the number varies, the diameter of the ring varies. So the diameter is directly proportional to the square root of 2n minus 1. So 2n minus 1 always gives us an odd natural number. So what we conclude here is the diameters of the bright rings are proportional to the square root of odd natural numbers. So this is the condition. Now what is the condition for the dark ring? So for the dark ring, d is directly proportional to root n. So it is directly proportional to the square root of the natural number. There it is odd natural number and here it is a natural number. So these are the conditions for bright fringe and dark fringe. Now how do you determine the wavelength, expression for the wavelength using this Newton's ring setup? So what we are considering here is a plano convex lens whose radius of curvature is r. And we are using a monochromatic source of light whose wavelength is lambda. Now, dm and dn are the diameters of the mth and nth rings. We are considering two rings, mth ring and nth ring, whose diameters are given by dm and dn. Now, using these diameters, how we are going to get the wavelength? So, we have the formula lambda is equal to dm square minus dn square upon 4 into m minus n into r. R, the radius of the curvature of the plano convex lens, is constant. So we know which is the mth ring we have considered, and suppose I am considering the 10th ring and the 5th ring. So the diameter of the 10th ring square minus the diameter of the 5th ring square will substitute here and we will get the value of lambda. So lambda is equal to dm square minus dn square upon 4 into m minus n into r. Now the next question is, why is the central spot dark? When we are talking about the Newton's rings, we have seen that the central fringe is always dark, and then you have a bright fringe, dark fringe, and so on. So what is the reason for that? Because we are seeing the rings in reflected light. There is always a path difference of lambda by 2. So in the reflected light at the point of contact, they suffer a phase change of pi. So the incident and the reflected light is out of phase. So whenever they are out of phase, we have destructive interference, and destructive interference gives rise to dark spots. That is why the central spot is dark. So the question here we are explaining is, why is the central spot dark? So why is it dark? Because of destructive interference. Why it is destructive interference? Because the two waves are out of phase. Why are the two waves out of phase? Because we are viewing in the reflected light, and at the point of contact, they will have to suffer a phase change of pi while getting reflected back, because the path difference is lambda by 2. For every path difference of lambda by 2, there is a phase change of pi, or for lambda, it is 2 pi. This is what you have to remember. Now, what are the different types of diffraction? We have understood diffraction, but there are different types of diffraction. So, the first one is Fresnel diffraction, which is named after the scientist Fresnel. Fresnel is the name of the scientist. So, what do we see in this type of diffraction? The source and the screen are at finite distances. Very important point. So, we are talking about diffraction is the bending of the light around the corners of the obstacle. So, there is an obstacle and the light falls on the obstacle. When it falls, so it is bending around the corners. But here what we are considering, the source and the screen are at finite distances which we can measure. Therefore, we don't need any lenses. So, lenses are not necessary as the source and screen are at finite distance. And here we are studying the direction of propagation of a light at a point on the screen. So, the incident wavefronts are either spherical or cylindrical. So, whatever the wavefronts that are being incident here, they may be spherical as shown here or cylindrical. So, this is all about Fresnel diffraction. Now, coming to Fraunhofer diffraction. What is Fraunhofer diffraction? The source and screen are at infinite distances from the obstacle. Suppose the source is at infinite distance from the obstacle. Then what do? We use lenses. So you see here, this is a lens. This is the lens which we are keeping for the light. If you are considering this is at a point which is at infinity, so the light from here will be directed onto the obstacle. This is the obstacle here, aperture or obstacle. When it falls, it will bend. And since they are at infinity, here also we are using the lens. And we consider this is the screen where we are getting the image. This is also placed at infinity. So the source and the screen both are at infinite distance. So we need lenses to study the diffraction pattern. And here the incident wave is always a plane wave, because all the waves that are coming from a far off distance, and then with the help of these lenses we are making them as plane waves. So these are the major differences between these two types of diffraction. Now compare the important phenomena of interference and diffraction. Since we have understood what is interference and what is diffraction, we'll try to compare what are the differences in these two phenomena. So in interference, what we see is superposition due to two separate wavefronts originating from two coherent sources. So the two waves that are superimposing are from two different sources, two coherent sources. But in case of diffraction, it is due to the secondary wavelets originating from different points of the same wavefront. If you recollect the diagram we have seen, the wavelets are from the same source. So, same wavefront. So they are superimposing on each other. And here the fringes normally have equal width. We have derived the expression for fringe width between two dark fringes or two bright fringes. Beta is equal to lambda d by d, and we have seen that it is the same for any two. But here the width between the fringes is never equal. So the width of the fringes is not equal. And all the bright fringes have the same intensity. Intensity is also same here. But here the intensity decreases with increase in order. Means as the order of the fringe increases, n is equal to 1, 2 and so on. Means as we go away from the central fringe, what happens? The intensity goes on decreasing. Then all the dark fringes have zero intensity because they're cancelling each other. We have seen in destructive interference, they are completely out of phase, and the resultant amplitude y is given by y1 minus y2, and therefore we get 0. They are of equal amplitude. So it is 0 intensity. But here the intensity of the dark fringes is not 0. So these are the major differences between interference and diffraction. Now we'll try to understand what is diffraction at single slit or the setup. We are going to, because we are not going in short answer questions, you will not be asked to explain the entire phenomena. You are asked only to explain the setup for a single slit. How diffraction occurs at single slit. So what we consider here is, take a parallel beam of monochromatic light of wavelength lambda that is incident on a narrow slit. So because it is a single slit, we are considering the slit here. This slit AB. AB here is the width of the slit, which is denoted by E. Width of the slit AB is equal to E. Now this is a source, that is the monochromatic light. Now light from this source is focused with the help of a convex lens. We are keeping a convex lens L here, and this light is focused onto the slit. Now when it is focused onto the slit, we know that there is bending of the light at the corners of the obstacle. So the light bends. So because of the bending, what we see here on this screen, this is the screen, we see a diffraction pattern. We see alternate dark and weak bright bands of decreasing intensity. We have already discussed in diffraction, the central one is always bright. So we'll have a central maxima like this. And then as you go, the intensity keeps on decreasing. These are different orders. Now explain the setup for double slit. If there are two slits, how diffraction occurs. So we are going to consider two slits here. This A, B is the first slit and CD is the second slit. So here we are considering it as E plus D. If D is the separation between the two slits and E is the width of the slit, so we are considering it as E plus D. So let a parallel beam of monochromatic light of wavelength lambda be incident normally upon the two slits AB and CD, each of width E and separated by a distance D. That is what we have seen. This is the source, monochromatic light. With the help of this lens, we are allowing the light to fall onto the slit. The width of the slits is given by E plus D. Each is of E and they are separated by a distance D. So we are considering the distance between 2 points on the slits. Corresponding points we take, it is E plus D. Now let the light, diffracted light, be focused by a convex lens L on the screen XY. So we are taking a lens L and we are focusing it onto the screen XY. Now the next one, what is plane transmission grating? Discuss its construction. What is a grating and how are we getting that grating? We are going to discuss. So what is a grating? large number of parallel slits of the same width and separated by opaque spaces. That means around 15,000 lines are drawn on 1 inch width of the grating. So I will explain you first the construction, then we will see the plane grating. If you take a plain glass plate and draw lines with the help of a diamond point. You take a diamond point and start drawing lines like this, parallel lines, very close to each other. So how many lines we are going to draw? 15,000 lines in 1 inch. So close the lines have to be. So take a plain glass plate and on that with the help of a diamond point, you start drawing lines. So the lines that you are drawing will be opaque. So they are opaque, means they will not allow the light to pass through them. But the region between these two lines is very small and we are considering it as E plus D, is transparent. No, these two lines are opaque, which do not allow the light. So the light can pass through this region, so it is transparent. So that we call as the slit. Slit means here the portion through which light can pass, and the width of each slit is given by E plus D. So what we understand here, the ruled lines are opaque, while the space between the two lines is transparent, and that will act as a slit. E is the width of each slit, D is the opaque separation. So when we are considering for each grating element, E plus D. Now let us discuss the long answer questions. We are going to discuss long answer questions. I am not going to give you the answers. I'll just brief you what are the points you will have to cover. In case of any doubt regarding this answer, you can refer to the video related to that topic. We have already uploaded the videos. So the first question, state principle of superposition of waves in case of two or more waves traveling simultaneously in a medium. So actually you will have to explain the phenomena because it's a long answer question. So you will have to explain what is the principle of superposition. When two waves of same amplitude and frequency traveling in the same direction, they superimpose on each other. They arrive at a point simultaneously. Then the resultant displacement at that point is given by the vector sum of the displacements. And you will have to draw the diagrams and explain the two phenomena. Next question, monochromatic light from a narrow slit falls on two parallel slits and interference fringes are formed on the screen. Sketch and explain the Young's double slit experiment. Means first you will have to draw the diagram. We have already discussed in short answer questions. We have a source. From the source, whatever light comes, it falls on the two slits which are placed equidistant, and the waves that are coming from these two will superimpose on each other, and you will have a series of bright and dark bands, and you will have to explain the entire setup. First, you will have to explain the experimental arrangement, what are the components we have, and what is the function of each, and how do we have the phenomena. You will have to entirely explain the phenomena. Next, give analytical treatment of interference of light and hence obtain the condition for maximum and minimum intensity by using Young's double slit experiment. So we are talking here about the analytical treatment. So when we are talking about analytical treatment, you have to first write what is the displacement due to the first wave, what is the displacement due to the second wave, what will be the resultant displacement, y is equal to y1 plus y2, and then you are deriving the condition for maximum intensity and minimum intensity. Means you will derive expressions for I max and I min. So all these you will have to derive. Then find an expression for the fringe width in an interference pattern and show that the fringe width of both bright and dark fringes is equal. So first what you have to do is you have to derive the expression for fringe width. So how do you get the expression for fringe width? We have already discussed. So xn plus 1th bright fringe minus xn bright fringe. This is the distance of the n plus 1th bright fringe from the central fringe. This is of the nth fringe. So when you do xn plus 1 minus xn, substitute the values, what you will get is the fringe width, beta, which will be given by lambda d by d. This is for the bright fringe. Here, you are going to substitute the condition. The path difference is always an integral multiple of lambda. So, for all such positions, you are calculating beta. And the same thing you will have to do for dark fringe also. So, for dark fringe, the path difference should be an odd multiple of half the wavelength. So, 2n plus 1 into lambda by 2. Again, keeping that condition, you will find xn plus 1 for the dark fringe and xn for the dark fringe. So, you take the difference, you will get lambda d by d. So, this shows that the distance or the fringe width between any two bright fringes or any two dark fringes is equal. In both the cases, you are getting the same value, so they are equal. Next, explain how the intensity and amplitude of waves result or lead to constructive and destructive interference. So, what we are going to talk here is, if the intensity is maximum, means it leads to constructive interference and that will be a bright band. When it is minimum, I minimum, that is due to destructive interference, it always leads to dark fringe. So for this, you will have to derive the expressions for I max. You will get 4a square, and for I minimum, you will get 0. So you will have alternate bright and dark fringes given by I max and I minimum. You can refer to this video for this derivation where we are deriving I max and I minimum. Next, explain how the energy distribution looks like in an Young's experiment taking the help of analytical treatment. So first you will have to do the analytical treatment. You will have to arrive at these expressions, and then you will also have to show the energy distribution. So how do you show the energy distribution is, so the maximum values is at 4a square and the minimum is 0. This is how the energy. We say that the conservation of energy principle is also obeyed. So wherever we are having minimum, this is being distributed along the maximum. So you will have to explain the energy distribution also. Next, summarize the conditions to obtain sustained interference and to observe good contrast in the interference pattern. So what are the conditions we have seen is, we have to take a monochromatic light. We have to take the two sources that are to be coherent, and the slit should be very narrow and they should be very closely spaced, means small d should be very small, and the screen should be kept at a very large distance, capital D should be large, and amplitude should be the same, therefore they will cancel each other. We will have contrast bright and dark fringes. And then we also were talking about the background to view them very clearly, because in order to have a good contrast. So the amplitudes and the background play a very important role in observing these fringes. Next, describe the experimental arrangement and the formation of Newton's rings. So you will have to explain the entire experimental setup, no? Starting from how you are taking the lens, the plano-convex lens, placing it in a glass plate, and how a wedge-shaped air film is formed. And when the air film is formed, how we are allowing the light to fall on it and viewing the reflected light with the help of a traveling microscope, and what we see is the Newton's rings. Everything you have to explain from the experimental setup and how Newton's rings are observed. Next, discuss the theory in the Newton's rings by reflected light and arrive at the expressions for the diameter of dark fringe and bright fringe. So whatever we have observed, that the diameter of the bright fringe is always directly proportional to the square root of odd natural number. So we have to derive this expression, and the diameter of the dark fringe is directly proportional to the square root of natural number. So all these things we have to derive. Explain how Newton's rings experiment can be useful to determine the wavelength of the monochromatic source used. So we have to derive the expression for lambda. Lambda is equal to dm square minus dn square upon 4 into m minus n into r. So you will explain the entire setup for Newton's rings, how Newton's rings are formed, derive the expressions for dm and dn. Then we will use the formula for lambda and calculate. Knowing the value of r, you can find lambda. Next, extend your understanding of Newton's rings experiment to determine the refractive index of a given liquid. So extend the understanding means the entire experiment, whatever we are doing it in air, because we have placed a glass plate on which we have kept a convex lens. So definitely there is an air film that is formed. So what we are considering, we have done it in air. Now, if the entire system is immersed in a liquid, then again you see the Newton's rings, the interference pattern, and calculate the diameters of the bright and dark fringes, dm prime and dn prime. These will be the diameters in the liquid. And then you can use the formula mu is equal to dm square minus dn square upon dm square minus dm prime here. So using this formula, you can calculate the refractive index of the given liquid. Then explain the phenomenon of diffraction and how Fresnel gave the correct interpretation of it. So first you will have to explain diffraction, how the bending of the light occurs at around the corners of the obstacle, and then explain with respect to Fresnel's diffraction. Means we are considering both the source and the screen are at finite distances, and then there is no need to use lenses. How he explained the diffraction phenomena, you will have to explain all the points. Next, diffraction phenomena can be divided into two general cases: explain and sketch the experimental arrangement. So the two classes here are the Fresnel diffraction and the Fraunhofer diffraction. Both the experimental arrangements we have to show and explain the differences between the two. Next, give the theory of Fraunhofer diffraction due to single slit, and then obtain the condition for maxima and minima. So you will have to explain the setup for Fraunhofer diffraction due to single slit. We have already seen the experimental arrangement for single slit. So then we have to obtain the condition for I max and also I minimum in case of single slit. Next, give the expressions for intensities for various maxima in Fraunhofer diffraction due to single slit and explain the intensity distribution graph. We also have to explain the graph here in case of Fraunhofer diffraction due to single slit. Then the next question is on double slits. The same thing, how we are going to extend it for double slits. If there are two slits, how is the intensity varying and what is the pattern? Next, discuss the theory of Fraunhofer diffraction due to n slits. Means if the number of slits are more, like in the case of grating we have seen. So in grating, what we have seen, we have drawn a number of lines around 15,000 lines per inch. Means the number of slits are more. So when the number of slits are increasing, if they are n, so how is the diffraction pattern modified? And what are the conditions for maxima and minima? We'll have to derive and show. Next, compare the important phenomena of interference and diffraction exhibited by light. So this we have already discussed. differences between interference and diffraction, and what is a plane transmission grating. So we have already discussed this, and the construction. So different parts you have to make. So first you will write interference and diffraction differences, maybe for 2 marks. And then what is a plane transmission grating? You will have to draw the diagram and explain how it is made and explain the construction for 2 marks. So it will be a 7-mark question. This is how the distribution of marks is going to be. Next, explain the theory of Fraunhofer diffraction due to diffraction grating. So diffraction grating you have to take, you have to explain the construction, explain the phenomenon of diffraction through the grating, and then derive the expressions. Then the last question in long answer, how will the diffraction pattern form when white light is used instead of a monochromatic source of light? Till now we have discussed that we are using monochromatic light, means light of single wavelength. Suppose in case we are using white light, means white light splits into 7 colors. We know the principle of dispersion. So when we are using white light, how the pattern is going to change? That is what we are going to discuss here. Now coming to analytical questions. Again, I am not going to solve the questions. I am just going to give the brief outline of how to solve these numericals. So the first one, 2 slits are separated by a distance of 0.2 mm. And they are illuminated by a monochromatic light of 550 nanometer. Calculate the fringe width. And the screen is placed at a distance of 1 meter. So let us see the steps of how to do it. First, you will identify the data. Small d, 0.2 millimeter. Wavelength, 550 nanometer. And capital D, 1 meter. So small d is given. Lambda is given, capital D is given. You have to find the fringe width beta. So we have a formula for beta. Beta is equal to lambda d by d. All the values are given. We have to simply substitute. Only thing you have to take care is of the units. So whenever we are talking about this, we are doing in the SI system. So the wavelength which is given in nanometer, we will convert it into meter. That will be 10 power minus 9 meter. And the distance between the slits which is given in millimeter, we are again converting it into meter. So just to simplify, you will get the answer. This will be the fringe width. So you can also refer to the video on numericals on light and optics. So you will get the solutions for all these numericals. Now in the second one, what is given? 2 coherent sources of monochromatic light of wavelength 6000 angstrom. They are producing an interference kept at a distance of 1 meter. So lambda is given 6000 angstrom and capital D is given 1 meter. And the distance between any 2 consecutive bright fringes is 1.5. Means beta is given 1.5 millimeter. What we have to find is small d, the distance between the 2 slits. So we have the formula for beta. Beta is equal to lambda d upon small d. Now we have to find small d. So we'll take small d here and beta will come here. So what will be the formula? Small d is equal to lambda d upon beta. So we are going to use the formula lambda d by beta. So what is lambda? 6000 angstrom, and we are going to convert this into meter. 1 angstrom is 10 power minus 10 meter. So this is a lambda. This is capital D which is given in meter, and beta which is in millimeter. We are going to convert it into meter. 10 power minus 3. So simplify and substitute, you get the answer. So this will be in meter. So the distance between the 2 slits will be If I can write it as 0.4 millimeter also is correct. Next, numericals on Newton's rings. In Newton's rings experiment, the diameter of the 15th ring was found to be 0.59 and the 5th ring is 0.336. Radius of curvature is 100. Find the wavelength of light. So we have a direct formula to calculate the lambda. So what is given here? Diameter of the 15th ring, 0.59 centimeter. Diameter of the 5th ring, 0.336 centimeter. Capital R, 100 centimeter. So here all the quantities are in centimeter. So we can continue doing the numerical in the CGS system. So lambda is equal to dm square minus dn square upon 4r into m minus n. So what is our dm? 0.59 square. What is our dn? 0.336. So square of it upon 4 into r is 100 into m minus n. M is 10th ring, n is 5th ring. Sorry, m is the 15th ring, n is the 5th ring. So 15 minus 5 gives us 10. So you get the answer and this will be in again meter. You can also convert it into lambda and write in angstroms. Now the next one. Newton's rings are observed in reflected light of wavelength 5900 angstrom. The diameter of the 10th ring is 0.5. Find the radius of curvature. Here we are not given the radius of curvature. We have to find. Lambda is given. So lambda is 5900 angstrom. Diameter of the 10th ring is 0.5. Means the ring n, we take it as 10. We have to find r, the radius of curvature. So what is the formula we have for r? dn square, that is the diameter of that nth ring. Here it is the 10th ring. So dn square upon 4n lambda. What is the diameter given? 0.5 centimeter. So we will convert the wavelength also into centimeter. 5900 into 10 power minus 8 centimeter. Just substitute here for lambda and for dn. And the nth ring is 10th ring. So substitute, you get the answer in centimeter. So you can as well write it as 105 centimeter or 1.05 meter. Any way you can express it. Next, Newton's rings are formed by sodium light between a flat glass plate and a convex lens are viewed normally. What will be the order of the dark ring which will have double the diameter of that of the 40th dark ring? So what we have to find here is what will be the diameter of the order of the dark ring which will have double the diameter of the 40th ring. So we are not given the diameter, we have to assume that it is double. So the diameter of the ring dm will be double the diameter of the nth ring. So here we are given for the 40th ring. So take n is equal to 40. So we'll write the formula for dm square and dn square and simplify. What we get is m by n. Because 4m r lambda upon 4n r lambda, 4 r lambda, because the source and the radius of curvature remains the same here. So we only have to find the order of the ring. So the relation between the two diameters are given. So dm is equal to 2dn. So dm square will be 4dn square. So just to substitute and you will get m is equal to 160. So the 160th ring will have the diameter double that of the 40th ring. Now one more. The diameter of the 9th dark ring in the Newton's rings experiment is 0.29. So we are given the diameter of the 9th dark ring as 0.29 centimeter. what will be the diameter of the 16th dark ring? You have to find the diameter of 16th dark ring. Lambda is given as 6000 angstrom. So in order to find the diameter, you need to know the radius of curvature. So using this, we will find first R and then substitute and get the value of the diameter of the 16th ring. So what is the formula we have for the diameter square? Dm square is equal to 4mr lambda, or R will be equal to dm square upon 4m lambda. So dm here is the diameter of the 9th ring, we are substituting, upon 4n 9th ring, and the lambda we have got the radius of curvature. So once we get the radius of curvature, we can find dn square. So dn square is 4nr lambda. So n here is 16 because we are finding the diameter of the 16th ring. 16 into radius of curvature. Everything we are writing in centimeter. So 39 into lambda. We have converted this angstrom also into centimeter. So we have got dn square as 0.14976. If we want d will be square root of 0.14976. That will give us 0.3869 centimeter. So we will stop here and we'll meet again in the next lecture. See you again. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.